Actually, if the title is too lengthy,
Okay. Okay.
it doesn't accept.
Mhm.
So,
President sir said he would like to speak for a minute, so we'll give it.
sir, live stream is ready.
Yes.
Anytime you want to start.
12:00. Yeah, we can start now. 12:01.
Yes, yes.
Namaste. Namaste, Geeta.
Namaste, sir. Namaste to everyone.
नमस्ते कुलकर्णी जी.
Yes. Namaste, Kulga. Yeah. Mithilesh ji, namaste.
नमस्ते नमस्ते अरविंद जी.
Ranjita madam, namaste from South Point School.
Namaste, sir.
Yeah. Please come on cam. Come on camera.
Yes, I am there on camera.
Yeah. No.
One
Ranjita
second,
madam.
sir.
Ranjita madam.
I will.
Yeah, yeah.
Hello. Sir, only the coordinators are there or even students will be there now?
Yes.
Students are there.
They're waiting. 3 schools to come. Prasadini, Dr. Prasadini, come on camera for a while. Yes, sir. Namaste. प्रेसिडेंट सर आ गए हैं.
Hello, sir. Namaste, Andy.
Yeah, Prasadini, namaste. So happy to meet you. And thank you for all wonderful things you are doing. That's great.
Thank you, sir.
Prasadini
Thank you,
comes
sir.
from
My
Visakhapatnam.
Sir,
Yeah,
namaste.
Vizag. Yes, namaste.
KGP Anandpuram, sir. Visakhapatnam district.
Visakhapatnam district. Okay, Andhra Pradesh. Yes, nice.
Thank you so much, sir, for
Thank
giving the
you.
opportunity.
We should thank you because you could make it. Enthusiastic.
Thank you, sir.
Yeah.
Thank you.
Chitra Madam, Namaste. Chitra Madam.
Namaste, sir. Sir,
Yeah.
we assembled here in the library seminar hall of Sri Ramakrishna Engineering College, and 84 students from 9th standard from Sri Ramakrishna Matriculation Higher Secondary School assembled here, sir. Thank you for all your support, sir. Are you able to hear my voice?
Yeah. Yes. Shall we start now? Or you want to wait?
Sir, can you hear me, sir?
Shall we make a beginning?
Here we are. Sir, can you hear me? Oh, Ranjita ma'am.
Okay.
Hello.
Yes, Ranjita Madam, Namaste.
Namaste, sir.
Yeah.
Sir, myself is Sanghamitra Roy.
Yes.
The coordinator, actually from senior secondary section, IPT member.
Okay.
So along with me, actually, Vikramjit sir, who is taking up secondary section classes.
Yes.
Both of us have arranged this meeting, sir. Okay, thank you. You can now carry on.
Shall we make a beginning?
Sir?
Rekha Madam. Rekha Madam will give the green signal.
Here we have Sanghamitra.
Myself is Sanghamitra Roy.
Namaste.
South Point School. Okay, show your face. Show your face. Show your
Start
face.
video.
And he is Vikramjit, the coordinator. You can start, sir.
Yes. Okay. I would like to, this is Arvind Kulkarni calling from Bangalore. And I want to say that WION, world is one. And we are seeing Indians from different parts of this great country. And I'm very happy to invite all of you to this group. Particularly happy situation is that schools are joining, groups are joining, and they have their screens ready. And I see at least 5 or 6 different schools already have joined, and 1 or 2 others will join shortly. Okay, the individuals meeting is one thing, but the groups meeting is a totally different thing. And let me welcome all of you for this quantum Zoom meet of we hope that this whole year this kind of things will continue with maybe short breaks on Saturdays, Sundays. We are working out towards that. This is our first experiment. We need your cooperation and blessings everywhere. Okay, with these words, let me welcome all the coordinators first, and with them the school children who have come. And I would like to invite Professor P.K. Ahluwalia, the president of Indian Association of Physics Teachers, who is always encouraging us to do what we do. So I will leave this to him. He will speak for a minute, welcoming all of you. Thank you.
Very good morning to all. Am I audible?
Yes, sir.
Okay. So it's quite an event, I would say, and it's nice that we have networked with schools across the country for a very special program, which is part of International Year of Quantum Science and Technology. It's IAPT's agenda that whenever there is something which is very special happens and we need to reach out to the young minds, we always try to create a kind of an atmosphere where we can meet together. I think this is a special program in the sense that have schools participating from every corner of the country to be part of this. There is a lot of rush I can see in the halls, which are visible to me right now. I'll just say in words that we are seeing today as the technology development, or when we are saying that we are living in the 21st century, that is because of sometimes invisible contributions of quantum physics. And it is all prevailing, all pervading, even when you are looking at your watch, say, which is a digital watch. Remember that quantum mechanics is at work. You are looking at the screens here. The screens have a lot of quantum mechanics at the back for the creation of the wonders around us. I think without quantum mechanics, we would not have been sitting in this Zoom classroom itself. So that is the way the quantum mechanics is influencing us. And there is a lot of excitement. Now, the purpose of these programs is twofold. One is to bring awareness about our very special programs which are internationally being celebrated. Second is that it should not just reduce into a mela, that we have gathered all and there are 100 students sitting and we are just watching. I have something special to tell you, that when you sit in such programs, you should always sit with a copy and a pen with you. And you should really make record of what you are listening. It is very important that we make notes when we are listening to such lectures. If you will just take these as an ordinary lecture, I think that you will be disappointed because it is a thought-provoking program. We want that it should excite you and it should not switch you off from physics. That is a very important point which I want to make. Because what you are going to listen to is sometimes beyond common sense also. And when something goes beyond common sense, sometimes our common sense doesn't really accept that so that easily. So please treat this program as a very special program where you require a very special attention. And it is not just, once again, I'm underlining that word which I used, a mela. It's a very special program. And don't just get switched off when you try to listen to some big words also, which you may be hearing for the first time here. You need to pay attention. And that is what I can say. I congratulate the organizers for this particular program. We would like that the coordinators of the schools should not just sit down here and watch the things. I expect that you will submit a report to IAPT, particularly to the General Secretary, who is very much here. Her WhatsApp number can also be shared with you. That what you have got out of such a program, was it meaningful or was it too small or too big or too complex? You must make your observation and let us know. I always believe in one thing. If you want programs to be successful, there are three mantras for that: feedback, feedback, and feedback. Unless you give us feedback, we will never get whether we are doing something right or wrong. And it may really lose the purpose with which we have come out with such a particular program. Once again, I wish each one of you a very happy participation, insightful participation, concentrated participation in it. And please do participate in the quizzes, etc., which are being shared with you. And that is also another way of getting a feedback. All the best, all the participants, all the coordinators, all the schools. Hats off to you that you have joined us. I thank coordinator Professor AJ Kulkarni and the team of resource persons who have really taken up a very tough task, I should say, because we have to bring down things to a level where students can appreciate when they are sitting in class 9 or 10 of a school. Thank you very much.
Thank you, sir.
Rekha Madam would like to say a word or two.
Sir, I will just wish you good luck. So, respected President P.K. Ahluwalia ji, coordinator of this QZS India program, Professor A.G. Kulkarni, my friend Professor Geeta R.S., who is also a resource person, other colleagues, I think I can see Ranjita Deka Madam, Limaye sir also, Professor Limaye. A warm greetings to each one of you on behalf of IEPT. I'm really happy to see such kind of a very ambitious program. I mean, this kind of experiment was never done. And thanks to Professor Kulkarni for taking this initiative and actually putting into action. Because looking at those classrooms, we are really happy. And if we can percolate to these kind of children of India, I think IPT's goal is very reachable within some time. And therefore, without taking much of your time, I wish good luck. All other things have told to you by our president, Professor Aluwalia. Do share your feedback. Do share your reports with me. I have already given my email in the chat box. You can record that. I've already posted a YouTube link. Those who are not able to join here, they can see the program later also on YouTube channel. That is IPT Central YouTube channel. With these few words, I wish a great good luck to this program, and I'm sure the program is going to be a very grand success. I wish all the children and the coordinators a very fruitful time for next 3 days. Thank you. Thank you so much.
Thank you, madam. Thank you.
Kulkarni
Geeta
sir
will
or
start.
Geeta madam, yeah,
Geeta Madam.
you can start.
Yeah. Shall I start, sir?
Yes, start.
Okay. Okay. Good afternoon to everyone. I am very thankful to the President of Indian Association of Physics Teachers, Professor P.K. Ahluwalia, General Secretary Rekha Gorpade Madam, and the coordinator for this Bharat Zoom School, very ambitious program, Professor Arvind Kulkarni sir. When he was going through all these things, I never expected that it would be that so many schools would be joining. So I'm very, very thankful to you, sir. And I am very thankful to all the school coordinators who have joined here. And please convey, because students, they would be sitting there. So a very warm welcome to all the students who have joined. Let them not feel that they are actually the most important part of this. And if it has to be interactive, and all the coordinators also, I just want to tell you that you can ask questions from the student side or from your side. You can always see to it that there is constructive interference, so that we can go ahead. There is not especially students, they have to ask questions. Only then this would be a success. And one thing that I want to say is, we have tried to bring it down, but quantum physics itself is like that. Some of the concepts may be a little bit difficult, but that will be overcome in the coming days by the students. Okay. So let me, without much of delay, let me share my screen. Can everyone can see, no, my screen?
Yeah.
Okay.
Geeta, can you make it full screen?
Yes, yes. I will make it. Yeah. Okay. So, one second. So this is Introduction to Quantum Science and Computation. So year of quantum science and technology. So this is very apt. You know, I would already a pre-test has been given to all of you, but still I would like to start, and some of the students, you know, if I would be able to listen, I would be very happy to some of the questions here. You know, right away starting with the topics, you know, might be too much for the students many times. So what is an atom? So there are options coming up. If students, I could, you know, let them go through that. And I feel that all the coordinators' mics can be unmuted so that we can listen to the students. All the mics can be unmuted because they're all teachers only. So anyway, yeah. So what is an atom means, I want answers from students. Would they be telling the smallest particle of matter, a planet, a large object, or a type of molecule?
What is the answer?
No. What is the answer? Students. One of the coordinators can convey it. There is no problem.
Vikramjit material.
Yeah.
Morning.
Geeta,
Ah,
I have one suggestion.
yeah. Let
Um,
them put it in the chat box. That would be
Either
best.
chat box or only when they are speaking, ask them to unmute. If
Okay,
simultaneously
okay.
they unmute, there is a lot of echo.
Yes.
Yeah,
I
because
understood. I
they
have
are
understood.
streaming it in their halls, I suppose.
Okay.
That is the reason I think everyone is getting the echo and the mixing of. So only when they want to, the children can give the question to the coordinator and coordinator can ask. But
Okay.
only when you want to speak, you just switch on.
Oh, that will be wonderful. That will be wonderful. Thank you. So I request all of you to mute, and then only when you want to answer, you can unmute and you can do it. So what is an atom? I'm sure any one of the, or you can put it in the chat box. I would be going through the chat box also. So I think many of you would have written the students' answers. So you can type your messages over there. So that would be very easy for me. And you can ask your students what travels faster, light or sound, just to, you know, bring them to the mainstream of physics here. That is the reason why these questions are being asked. Let them come to the physics frame. This is what I have in my mind. Okay. So if you can put it in chat, it would be very good. That would be good. Then you can ask your students, an electron is smaller than grain of sand, true or false? So that can be asked. So whatever answer they give, you know, you can put it in the chat box. Then, you know, what is a bit? So because finally this is all leading to quantum computers. So we would like to ask this question also. So a small piece of paper, a type of circuit, a coding language, basic unit of information in computing. So like that you can give. And computers can solve problems if we tell them exactly what to do. True or false? So this can be asked for the students. What happens when we split a beam of light. Whether it narrows down, whether it broadens. So these kind of things students can think and they can answer. And what is the word quantum means? It is very important because we are starting with quantum mechanics. Therefore, the word quantum meaning itself should be very important to all the students. What do they mean by the word quantum? Okay, so let me see if so one or two answers will come from students, not from teachers, please. I want the coordinators to put the answers as given by the students. That is the most important thing. Okay? So what do they understand by the word quantum? Okay? So if you can put one or two sentences over there, it would be, it will give me an idea. Okay? All right. It is okay. So you can take your time and it can be done. And which type of wave requires a medium to travel through? So this can be asked to the students. As it is coming, whatever you have listened from your students, you can. In the photoelectric effect, light behaves as. This is, many of the students might not know about that, but still, some general knowledge, if they have, I would like to know their answer. What happens when waves from two sources meet and their crests overlap? So, then the speed of a wave is given by. And what property of a wave determines its energy? First of all, a wave itself, many of the students might not know about waves itself. But still in their mind, some things would be there. Some of the, whatever they have listened to, maybe they have some visualizations. So these are just, the previous one and this one, just their understanding. Okay. So then let me, because time, I don't want to spend too much time on any of, I'm sure teachers, as coordinators, you would have done these things. See, classical mechanics is what is being taught to you in schools. See, from now onwards, I will be addressing to the students rather than to anyone else. So, you have learned about, motion, and then some forces. So these kind of things you have learned. So all these, they are based on Newton's laws of motion. So the 3 Newton's laws of motion. And if I ask you to state these laws, I'm sure all of you will do it without any hesitation. Whether we have understood those laws or not, that is different. But all of you will say. And then you have in motion, you have learned about some of the equations. V is equal to U plus AT. V is the final velocity. U is the initial velocity. A is the acceleration. T is the time taken. And S is equal to ut plus half at squared. And if you know the position, how to locate a particle, and if you know how to locate its position, then you can predict what will be its behavior after some time, because we have definite equations for that. And all these things you have done. So these kind of things, so based on Newton's laws of motion, this is known as classical mechanics. More or less, even landing a rocket on Mars, the classical mechanics helps us. There is all these rockets also work according to the equations available in classical mechanics, more or less. Some of the things might require a bit of quantum mechanics equations, but more in general, they will all be there. Then how the planets move and this gravitational forces of attraction, all these things normally they will all work according to this Newton's laws of motion, or what is known as classical mechanics. That is what you are learning. And see, it deals with macroscopic. Macroscopic means how big you might be thinking. From human scale of point of view, we would be thinking so macroscopic. But quantum mechanics actually deals with microscopic. That is where Newton's laws of motion, they have some difficulty. Now, when we want to apply to the motion of microscopic particles, then we observe that this Newton's laws of motion might not be able to properly predict the motion of these particles. See, you can think of examples of microscopic particles like atom itself, even a small grain of sand. It can be a very small amoeba. It can be a paramecium, or it can be electron. You have heard of these names: protons, neutrons. They all make up atoms. Protons, neutrons, and electrons. So there, this classical mechanics might not work. Now, classical mechanics, as we have told, whatever we are studying, the motion of particles. So it works, it is based on Newton's laws. But here, Schrodinger's equation also, there is one more formulation known as the Heisenberg's matrix formulation. I have not written there, but Heisenberg's matrix formulation is also there. And here, any amount of energy, see, we don't restrict. I can give any energy to a particle, but here it is not so. Only some amount. Say, for example, you have a rupee. Rupee means its quanta is 1 paisa. So that means 1 paisa only. You cannot have 1.1 paisa into something in a rupee. It is 1 paisa, then 2, 3, like that. So, similar to that, here also there is a quanta of energy that can be taken by these microscopic particles. So that means to say that is where the word quantum has come. So some steps of energy, it will go in some packets, no in between. It can go in integer multiples of that minimum sized packet. So that is the important difference here. So you can kick a ball with any energy, but here it is not so. Then why it is not, we don't observe? Because for macroscopic particles, this is not required also. So we will take it as continuous here. And the state, that means how the particle is, maybe its location, where it is located, how much energy it has, or what it is doing. They are all known as the state of the system. So that can be defined by its position and by its velocity. But here, the very nature itself, you will find that it cannot be specified exactly. In quantum mechanics, it is counterintuitive. That means it is, it is not according to our common sense. Therefore, we say that it is counterintuitive. And here we are certain. See, suppose you are walking. In 1 minute, you are certain that I will cross that gate. certainty is there. But in quantum mechanics, no certainty of these things. So it is only a probability. You will say that probably in 1 minute I will cross this gate, or I will go to that position. So there is no certainty involved. So that means to say all of us have to come out of box and think about quantum mechanics. So we should not only look through our classical eyes and listen only through our classical ears. So now you should develop a quantum eye, quantum ear, and quantum thinking now to understand quantum mechanics. Okay? So it may not be to your common sense. It may be totally a new concept. Therefore, you have to come out of that. Now, in classical mechanics, also, two things. One is wave and another is particle. So, what is waves? It can spread in space and time. See, waves are not localized. So that means they can spread. Think of sound wave or water waves. Suppose you put one small stone in a pond, then you can see the water waves. So you will see that the spreading, it is not localized. But whereas particles, they are localized. So they are at one position in a given time. So, and moreover, waves can pass through each other. Suppose you take a rope, you move it up and down. The opposite side of the rope can be held by your friend. He or she can also move it up and down. You will see that both the waves can pass through each other on the rope. This experiment can be done by you. Okay, but particles localized means they are at a single position at a given time. That is the meaning. So they cannot pass through. Suppose they want to pass through. Suppose two stones will come. They cannot pass through each other. They will collide. Either they will shatter or they will, be scattered. Okay, so they will be scattered. So these are the basic differences in their behavior. So you can see that particles, this blue will collide with the brown, and then they have all shattered into pieces, or they can just scatter around. Okay, so this is there. Now waves, what do we mean by them? You will show me with your hand, if I ask what is a wave. So like this up and down movements. See, in your mind, it should not be, suppose you have seen water waves. There can be circular spreadings also. So what is that? The maximum, they are known as the crusts here, and the minimas are known as the troughs. So when they are spreading, so the waves will, they will have maximum displacement. So that is known as the amplitude. So that will be the crest of a wave, and the minimum displacement on the other side. So that is known as the crest of the wave. And you can describe a particle by its mass, by its length, breadth, etc. Similarly, a wave can be described by means of its wavelength, frequency, and then a velocity. These kind of things, it can be described. Okay? So waves are produced by the up and down oscillations. Okay? So, in the case of electromagnetic waves, of the electric and magnetic fields, in the case of sound waves, it is the up and down motion of the particles of that medium. So they will create pressure waves. So like this, a waves, the disturbance will travel through the medium, and that it carries energy waves. Particles, they themselves, when a force is given to them, they themselves will transfer the energy from one position to the other position. So these are the, okay. Then material objects, we see that this is how falling ball. Now, waves can pass through each other. This is what I was telling you. See, the left side, one wave has started. From the right side, another wave has started. They meet. They will become maximum and then they will continue. So, they can pass through each other. So, they regain their original form. So, as they pass through each other, they can cancel or they can add up. So, both are possible. Okay. Now we are going for our, so this was about the classically whatever we had in our mind. Now once we enter into the quantum world, that means microscopic world, the sizes, if you just to see the sizes, can you see that the galaxy cluster is so big in terms of meter? You might have observed a meter scale. So you have to keep how many? 3, 1, 2, 3, 4, 5, 6, 7. So that means 7 into, in front of 95, there are 21 zeros. So that many scales you have to keep. If at all, if a galaxy cluster has to be measured. Then our universe. But look at the molecule, silicon molecule. It is so small, 0.000000001. Then oxygen molecule. Then quark. Quark is a, don't worry about that. That is also a, from which the electrons are constituted, or a proton is constituted of these quarks. So these kind of things, they are all very small. So the earth size is there. So then the solar system size is there. So you can see that this is, but in these type of very small things, that is where the classical or the Newton's laws of motion, may not, they are unable to describe the motion properly. Okay. See, you will see the floor, everything as smooth, because you see it as a continuum. But the moment you see something with a microscope, you can see that the floor of your classroom, for example, is not so smooth after all. It can show you the grains and all those things. At that level, or your skin, it is appearing very smooth. But the thing is, the moment you see, you will see that there will be many hills and valleys on your skin also. And at that level, the all this position determination, velocity determination of those atoms that make up our skin molecules might not be so easy as using the Newton's laws of motion. So how big are atoms? Democritus was the first person who tried this, and he showed that it is very small, 10 to the power of minus 7 centimeter. Divide 1 centimeter into 1 crore parts. So that one part would be the size of a centimeter. So then that is why we have, instead of telling 10 to the power of minus 7 and all such things, we have a scale known as the nanometer. So nanometer means in your mind, don't worry about 10 to the power of minus 9 and meter and all these things. In your mind, it should come that it is extremely small. It is of the size of the atoms, molecules, these kind of things can only be described in terms of these nanometers. So we have introduced, in the meter itself, how a very small part of the meter has been named as nanometer, micrometers. So these kind of things. Okay. Now in quantum world, so what are the implications? So when we are talking about in this quantum world, that means in this small microscopic world when we enter into, the classical ideas were, were not working. There were two very famous experiments. One was the photoelectric effect. When light was incident on some metals, from the metals, the electrons were coming out. That was known as the photoelectric effect. So, electron coming out, electric. Photo means light. So, this was known as the photoelectric effect. So, this classical, people thought Maxwell had done wave equations for light. So, waves, people had understood everything, all the wave phenomena, people had understood. Particle were separate entities. They were understood in terms of Newton's laws of motion. So, people thought that we know everything. But when this photoelectric experiment was done, and there was another experiment by the name of black body radiation, when these were done, the classical ideas were unable to give. The wave theory of light was not able to explain this photoelectric effect. So then, to explain black body radiation, Max Planck, he was the one who coined the word quantum. What he did was, it seems in desperation, he took the energy of light in steps, quanta. That is what I was telling you, like a rupee has one paisa as a quanta. For the energy, he took for the energy of the oscillators of light, which were producing light, the oscillators which were producing light, he told that it has to come in packets of energy. And then he was able to explain. Then Einstein was able to explain the photoelectric effect using this quantum, that light behaves as particles. So Newton, in the beginning, he had thought light as particles. But then there were phenomena of some of the phenomena like interference, etc., which could only be explained as by the wave theory. But now again, we observe that photoelectric effect can only be given by considering light as a particle. So this particle of light is given the name photon. So a stream of photons, the light particles, are given the name photons. So that means to say now, light is coming as a stream of particles, then photoelectric effect could be explained. Black body radiation could be explained. So their interactions. So this study of small particles, quantum physics involves with these things. It is the key in unlocking these microscopic worlds. And remember that rules that is why now we observe that light can behave both like a wave and a particle now. For some of the phenomena, even in quantum physics, we still use light is behaving like a wave. But some of the other phenomena like black body radiation and photoelectric effect, we are invoking that light is behaving like a particle. Therefore, rules are different here. So in classical physics, objects are in definite position. You know their trajectories. So how they will be moving. If they obey V is equal to U plus AT, how it will be obeying, what trajectory it would be going. I want you to answer these questions after some time. I will be asking. And then current, you know what is the current in the system. So depending upon the resistances, etc., you can predict in the future. But in quantum physics, there are new rules. This is the first thing you should take to your mind. And particles, there is no definite state for them. They can exist in many states. So looks like magic. I can be in two different positions. So it sounds like magic to us, isn't it? But till it is measured, the quantum objects can be in multiple states. I have told you that state describes what is, maybe its location, or maybe what is its momentum, etc. So what state it is in. So they are measured. And in quantum physics, no new rules have to be done. They can affect each other even if they are far apart. Suppose an earthquake happens in, let us say, in Antarctica. We are not worried here in Bangalore, correct? We feel that that earthquake, see, maybe internal tectonic plates and all that. But one thing is for sure, our buildings will not fall if some earthquake will happen there, isn't it? So that means to say, in quantum mechanics, even if they are far apart, one of the state can affect here. So these are all, sounds like, counterintuitive, contrary to what we expect. So it says that quantization means energy, momentum, all these things will come in discrete, in steps of some small quantity. Suppose you take one quanta, it will all be in multiples of that. 1 times that, 2 times that, 3 times that, not 2.2 times that. Okay? So this is there. Then quantum physics talks about wave-particle duality. So light can exist both as a particle and as a wave. And there are what are known as uncertainty principles. Let us not too much worry about that at this stage. In future classes, once you are introduced to these things, let us see. So this is the quantum, so given by Einstein, as I was explaining. So energy of a wave is given by a different expression, whereas the energy of a photon is given by a constant known as h multiplied by the frequency of light. So this expression is specially given for photons. So packet of energy or photons, see, we are impinged by photons. All the lights that are there in your classroom or whatever, all the light sources, your face is impinged by these photons. You are not feeling them. They are so small, the particles of light. So even if you touch your face, you won't be able to see anything. Okay? See, let alone photon, we are even unable to feel breeze also. Okay? So then, the next thing is, if light is a wave, can have particle nature, as shown by Planck and Einstein. If light can behave both as a particle and a wave, can material particles? See, what do we mean by materials? Matter. See, in layman's language, it is something which has mass and occupies space. So that is known as matter. Material particle means something in layman's language only, like how you have learned. Say, for example, if you take yourself, so you treat yourself as a material particle. So you have matter, you occupy space, isn't it? So then, that means, can matter also exist as wave? See, it is impossible for us to think that we appear as waves, isn't it? See, we are there. So, de Broglie proposed that matter can also exist as waves. See, it is for our classical thinking, it becomes almost, how is that I am a wave? Because I'm highly localized. See, the very explanation of particle itself is that we are localized. We are at a position and the next position, we are highly localized. But waves means by their very nature, they are not localized. So that means to say, these electrons, so that means to say, are they not localized? So these were the things. So that is why I am telling you, you have to come out of your boxes to think. You should not see with our classical eyes now. We should see at the quantum level. So how is electron? It can appear both as a wave and a particle. Okay? When you are not measuring it, it will be doing things like a wave. The moment you measure, it behaves like a particle. Isn't it very strange? Isn't it? See, quantum mechanics itself, makes things difficult for us. But I am sure at your age, you would be able to visualize these things. At the microscopic level, you should be thinking about how these small things are going about. They are moving so fast and all these things. So they need not be localized. So when once you think that electron need not be localized, you can be thinking that it can behave like a wave. This is the important thing that should come in your mind. Okay. So that is why I had one cartoon here. So that means I am both a particle and a wave. Okay. So even matter, ourselves. Okay? So we can appear. So this is the particle nature. So that ball is a particle nature. So wave represented as crusts and troughs. So particle, small balls type. Then waves, you can see that this is how. Then this is wave-like and particle-like, and then both wave and particle. So this is the picture that now we have. So not only light, why only light? Even matter can exist both as a particle and a wave. Okay. So summary is there now for you. So wave nature, electromagnetic wave, particle nature, photon for light. Then particles, wave nature, matter waves. Not only electron, protons. When atom itself can exist as a wave, then obviously what are all the things inside also. Then particle nature. Particle nature, you have many examples for matter particles. Okay. So this is there. So then classical, but see, this world deterministic should not be thinking, though there is no need definite about their position, etc. But whereas quantum world is only probability. That means you can only say, yes. See, suppose you have come to your school. Your parent, your mother would be thinking at home, yes, my child is at school. But where in the school? So she will be thinking of all probabilities. She will be thinking, she might be in the corridor, she might be in a class, she might be in the library, she may be talking to a friend, near to the gate. Okay. So this is like probability. But once we observe that you are actually in the library, the probability has gone. We have measured, yes, you are in the library. But till then, everything is a probable state. Okay. So that means in classical mechanics, all things will go, they are independent of the observer, they will be going. But in quantum mechanics, it is all observer related also. Okay. So observer and observed, they are tied together. Now there is a problem for you. Now there are a set of boxes. Matter, light, particles, waves, and then a photon, dual nature, all these things are there. Now I give you a small rock. To which box you will put it? To which box you will put it? You can put it in the chat box, or one of you can unmute and you can say. A small rock.
Matter.
Yes. Who is telling? Matter. Very good. Very good. I am very happy. Then what about light? So light box itself we will put. So there is no problem. Particles you will put it into the particles box. Waves you will put it. Then, a beam of light from flashlight. Where you will put? A beam of light from flashlight. Where you will put it? Either you can unmute and answer, or you can type. I am looking at the chat box. Okay, fine. Very happy. Then what about tiny balls? You can go on typing the next things. Particles, correct. Beam of light. You want to put it in waves also? Fine, fine. Yes, this is where I am, this is how you should develop. Very good. Then tiny balls in particles, mini electron models. Where you will put? Photon emitters, where you will put? Yes, correct. Tiny balls, particles, correct. Waves, correct. Then photon emitters, very good. This is what I was looking into. You have put it dual nature. So I'm very happy that you were able to put these things.
We will
Yes,
break
now,
for 5 minutes. That was all.
yes, that is what I was about to tell that. We can take a 5 minutes break here.
Okay.
And if some of the students feel that they have to ask, through the coordinators, you can always say, or you can say whether it is fast or slow, or you are following. So these type of things also can be put it in the chat box. Yes.
Yeah, pause the YouTube for 5 minutes and then.
Yeah, I will stop sharing for time being. And
no,
even otherwise, let it be there.
I would like
no
you
problem.
to start because you are.
Let them all be taking. After 5 minutes only, I will start.
No, she has already stopped. She has stopped.